Okay, this is lecture 25. Do you have any questions from yesterday? And so there was a question yesterday after the class. So let me just write the question here that I have a phase error detector and a loop filter by the VCO on the side. Okay, and I can have a divide by N and an input. Right, so this I have V in and I have V out. So if you have a divide by n factor, then surely your f in and f out are related by your n factor. Okay, so let me just, in place of f in, let me just call this as f ref. Okay, so we know that v in is equals to something as a in sine or cosine whatever omega ref times t, and v out in a locked case a out times sine of omega out t, which is the same as sine of n times omega ref times t. Okay, and when we did all the phase noise analysis, we looked at a loop gain where loop gain of this loop which I have shown, loop gain with respect to omega. So that was like for a type 2 and order 3, we had something kind of this. And this was the unity gain frequency. You have a 0 here and a third pole here. Okay, so all this frequency analysis which we showed was with respect to the DC. Means loop filter itself, when we use any RC, that is the filter response with respect to the DC frequency. Okay, now the question is this, that I am injecting something at a reference, means we have seen the reference disperse. So let's say I injected a reference, something at a reference frequency Vref, some voltage or some pulse which I am injecting at every reference. Tref is the time period. Okay. Now the thing is, I showed that at the output of the oscillator, so if I just extend this frequency axis, okay, so somewhere here I will have n times omega ref, where my final output, means the output of the PLL, will be at n times omega f ref, and then I have the reference is per plus minus reference frequency away, right? So this is your at omega out plus omega ref, and this one is at omega out minus omega ref. Okay, so this one is the output voltage spectrum. So I just extend the same frequency axis to show that what's the confusion here. So the confusion was that the unity gain bandwidth of the PLL, which is omega u, is surely lesser than omega u. Normally we try to have less than 10 times, sorry, omega ref by 10. Okay, so let's say your omega ref is occurring somewhere here, just for example. So unity gain bandwidth is this. Okay, now the closed loop response, so let me plot another here. The closed loop response of the PLL from phi in to phi out will be DC, and so that will, so let me just plot it. That will show a minus 3 dB whatever. It shows a minus 3 dB at omega u, right? So this, and this value is 20 log of n. This is the closed loop response phi out by phi in for the phase. Now, if my bandwidth is much lesser, or bandwidth is less than f ref by 10, and my reference frequency, or the reference the disturbance which I am injecting into the PLL is at omega ref, and the spur which I am looking it as n times omega ref plus minus omega ref, right? So the confusion is whether the suppression which I am going to see is on the part is this. Will this be the suppression or what? Pardon? No, so that's what I am. Okay, let me repeat what I said and let me see what you saying again. So you see that the minus 3 dB bandwidth of the PLL, which is omega ref by 10, is much lesser than the reference spur which I am seeing at the output. Okay, so I am applying a disturbance in the PLL at every reference frequency, and I am looking at the output spectrum at n times omega, means output plus minus omega ref. So the question was whether the suppression which you are going to see, depending on the where my reference is and where my bandwidth is, will it be the suppression at omega out plus omega ref by, so let me just put whether the suppression should be this or it should be this. No, the phase transfer function is with so that is phi out by phi in. But the confusing part will be the loop filter you are not considering with respect to the carrier. So the loop filter part which you are still considering is having that is having a zero at your whatever lesser than omega u, which is real, which is nothing which is being translated. So there is nothing like shifting the frequencies in the loop filter. Yeah. Yeah, it is actual, but the confusion is that if this is the filter in the loop, why am I not seeing the suppression? Okay, so yeah, means that is the case, but the confusion is valid to arise. Is that was the confusion for you, right, yesterday? Okay, so the thing is, let's say whatever filtered you are getting from here, uh, so whatever filtering part you are getting from this when you are applying omega ref, means you can see whatever you are injecting in this PLL at reference frequency, when it comes at the input of the VCO, right, that voltage itself get translated by the VCO to the higher frequency. So you say, so let me just say call whatever V noise reference you get here at your reference frequency filtered by your loop filter at the input of the VCO. So suppression you can get. So whatever means delta you are injecting means it again depends what is the amplitude of V and V noise at the reference frequency, exactly you are injecting or being applied to the VCO. So for a given VCO, V and at reference frequency, this gets translated to the output frequency with plus minus F out. I think this is, so if I write V out is A sine of omega naught omega out T plus KVCO times Vn ref times dt. And Vn ref is the filtered portion which you are seeing here, right? So now you see that the spur which you are seeing is the translation of the filtered voltage at the output. Okay, so this picture will not be the real suppression. Huh? Yeah, but when you are reducing KVC, your bandwidth, effectively you are changing the bandwidth. So the thing is whether I have this as bandwidth, or let's say this as bandwidth. It all depends. So it depends. So let me just show you two ways. One way to reduce the spur is if I have, okay, this is going slightly crazy. If I have this one as bandwidth, right, means I shift the unity gain frequency, I reduce the bandwidth. The other one is, so okay, this is, let me pick up another color. The other one is if I shift the pole after the unity gain frequency, means I sacrifice my phase margin. Then I can have a better reference. And this we have seen when we are discussing the charge pump, that the placement of omega P3 is actually helping you to suppress the reference spur, but at the same time it is causing a reduction in the phase margin also. Okay. Any questions on this? Yesterday's class? Yeah, okay, sure. So let's continue with our yesterday's discussion was on oscillators. Okay, so what's the previous? Okay, so let me draw. There's a maniatic cell, right? Okay, so this should not happen. Okay, so at the very end, we were looking for the symmetric loading for our delay cell for the ring oscillator, and this was the cell which I drew at the very end. This is V control, VDD, this is I, and the potential difference is VR. And if we work out, and this is all with respect to all when we assume that these transistors are following the square law. So this one, so let me, okay, okay, so this is I versus VR. Okay, so this is the characteristic for the I versus VR for this cell. Right, right. Both are square law actually. So the resistive part, which that's what I am. That's a slightly difference there, right? So yesterday when I wrote these, since I wrote them already, I will not try not to write it again. So you see the first part, the equation which I wrote here, this one, right? This is a parabola with your downside parabola. So it is not a linear region. Okay, we approximate it to a linear region when we consider that okay, VR is very much smaller than the other part. That's when we consider. Okay, so this is a downward parabola. This one is an upward parabola. Okay, and the linear region is only in between, which I okay. So I basically amplified here. So let me just do the same thing for today's one, that depending on where your threshold voltage is occurring with respect to, so this terminal is, okay, what is this we need to find out. So let me just say, in case your V threshold voltage is lesser than the center point, and where the saturation for the M 0 and M1, saturation for the M0 transistor takes place, that is VDD minus V control minus mod VTH. So this point is actually VDD minus V control by 2. It's a midpoint. Okay, and if this is the if VTH is not coinciding with the VDD minus V control, so this should be okay. This is the midpoint of this. Then you will have a somewhat linear region. Okay, yeah. So the thing is, if I have a different V control, let's say V control is lesser, then my region, my center point, and all those things will vary like this. What do you mean by around the center point? Uh-huh. No, 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 no. So that doesn't happen. So, okay. So you see the first one, which is at the uh, downward parabola, right? You have the resistivity with respect to VR, which is linear, which we have seen before. Then at the other point, you are having a directly relation with VR that also it's not an infinite value. Yeah, it probably it can. Uh, I do not. I do not see means if you see this, but at the center point means this is means they. It's not like there's a jump in the value. It's all continuous. What do you mean by jitter at only the zero crossing? Uh huh. Okay. At zero crossing if it has a large enough R. No, but this R is okay. So what you are saying is, let me just back to this curve. Okay. So okay. So what you are saying is that during transition, when both of them are having the same current, at that time the resistance of this value is actually very high and resistance of the output load is very high, and then it is going to cause you the at that time it is going to cause you a very more noise. I do not, so let's look at what the resistance is if that's the case. So okay, so what we have at the linear means before the linear region we have kW by L VD minus mod VTH minus V control times VR minus VR squared by 2. Okay, and what will be the midpoint of this? Huh? VD minus V control, VD minus V control by 2. The midpoint of this I am looking at. These are the absolute values, right? So this will be VDD minus, is anything wrong with this? No, right? So that is the midpoint. And this is the, this region. Then in the other region, what you have, pardon? Midpoint, no, this is with respect to the x-axis. Okay, this is like finding, so let's say this is 3 and this is 5. What's the midpoint? Huh? 5 minus 3 by 2, that is 1. So this is the midpoint, right? So okay. So the other one is kW by L into VDD minus mod VTH. No, I'm just right. Sorry, there's another this V control. I'm just writing it so that we see that the derivative is continuous or not. That's the thing, whether the derivative is jumping VR plus mod VTH square by 2. Okay. So in case I have the linear region, then I have this kind of thing. I may have it, right? Means if I'm drawing with respect to VR, and this is kW by 2L into plus VR minus mod VTH whole square. Okay. So one thing is, at the midpoint you do not see any jump. This is straight line. You will have the constant slope. At the point of wherever I have this VTH coming, that is the point. No, so the thing is, why am I looking for the discontinuity? Whether the discontinuity, your resistance is going pretty high or not. No, no. Can you repeat again? Yeah. Right. It's going to be the smaller. So because you enter a saturation region. Yeah. But when you add a diode, then you are having a parallel path, right? You have worked. Did you work that out as resistor? Yeah. So the thing is, it might be showing a higher resistance. That's why I said that if we look at a derivative part of it at the point or discontinuity there, then we can see if there is a higher resistance or not. Okay, and it might be contributing more noise. Which, if it is having a higher resistance, we need to look at how much more noise does it contribute. So why don't, okay, let's make this as an assignment to see how much noise does it contribute, because I haven't seen it in that as such manner. But the way should be that you look for any discontinuity in the incremental impedance. Okay. So anything else on this? So the thing which we started was that this kind of loading is having a symmetric nature on the around the center point, and the symmetric nature or odd symmetry around the center points helps in improving the power supply rejection ratio. Okay, and one is the power supply rejection ratio, another is the loading itself, that your R1 and R2 are, they do not change, they keep the average, the swing the same. So what I mean, let me just show you this way, that if this is the center point, and if you take delta I minus and you go delta I up, okay, if you are swinging between plus minus delta I on the two sides, the final swing which you will find V out will be VDD minus V control. This you can work it out. So the way to work out is that you know what is the midpoint of this, what is the control voltage and the current. You find the VR voltage such that your delta I are lower, and find the other VR voltage such that your delta I is higher. So you will find 2 points. This is VR low, and this one will be VR high. And you can find the difference what is VR low and VR high. Okay, with respect to the midpoint. So this one I worked out, which was VR low plus VR high is VDD minus V control. Okay, and we know that VR low is something as VDD minus V control by 2 minus delta V. You can call this as delta V1, and VR high is VDD minus V control by 2 plus delta V2 is the same. VDD minus V control. I think this is the relation which turns out to be. Means this one. Okay. So delta V1 is equals to delta V2. So this has a symmetry on both the sides. So this is the one where you can have the swing fixed even when you are having changing the currents. And the other one is at the incremental. So let's say you are operating at any given point, means you are, let's say you are operating at this point, sorry, this one on the two nodes, and then you have the power supply noise which is coming as a common mode noise. So this is going to change the resistance. Okay, but the change in the resistance on the two sides is the same. The derivatives you will find di by dv will be the same. Because of that, you will not see you will not see the noise coming from the supply to the output nodes. Okay, anything on this so far? Okay, so to conclude all the low swing oscillators, because we have seen only that so far. Okay, they had limited output swing, constant current consumption, then so the limited output swings requires that you need to, in order to get a clock, in order to get a full swing clock, you need a low swing to a high swing conversion. Swing conversion means it requires that. Okay, it has a constant current consumption. So actually it has, the current sources are always on. So you have a poor phase noise. But in case you are using a differential cell, then you will have a better PSRR, power supply rejection ratio. Okay, and your tuning range is limited by the nonlinear resistors and others. Anything else is there in this low swing oscillators? Okay, so we will see how the large swing oscillators work. Try to see what are the pros and cons for them once we have seen the low swing oscillators. Okay, so for the low swing oscillators, I have very well used the Barkhausen criterion and showed you the gain and phase Barkhausen criterion for oscillation. For large swing oscillators, it is difficult to show that because that is not a linear system itself. Okay, so let me show how do you get the frequency of a large swing oscillator. So this is an inverter ring. So let me, without first an inverter ring, let me just say this in and out. And let's say you stimulate this chain of inverters with a clock frequency. and this is in signal. So let's say A, B, and the out. So A signal will be somewhat delayed from the in signal which I applied. So let me make it like this. This one is okay. Then in response to A, I will have a B signal going high, then out signal will be low. Okay. I just drew the whole waveform such that all the parameters work out fine. So the delay of each inverter will be the same. Okay, because I'm using a same inverter ideally. So this is TD delay. So you see that the edge, this one leads to this leads to this, and this leads to this. Sorry, edge leads to this. Now you see that the falling edge of the input, which is this, is coming in an absolute time scale coming at the same time as the falling edge of the output, right? So if this happens, then ideally I can replace this edge here. Okay, that means the time, or whatever the, if t was the period at which I was trying to trigger my delay chain, if t by 2 is equals to 3 times the td delay, then I can ideally I can close the loop. Okay, so in this case the frequency of oscillation, or if when I close the loop it will continue working on itself. So the frequency of oscillation is 1 by t is equals to 1 by 6 td. This is normally you will see in case of ring oscillators. Okay, and the output swing. So okay, this is the way I can show that this chain of inverters can be converted to an oscillator. And what is the swing at the outputs A and B? Full swing, because you are, so if I take one single inverter, it means at one time, if this signal goes from, sorry, low to high, at that time whatever the capacitor is here, you will be charging this capacitor to VDD, means this node will go to VDD, and in the other case you will be discharging the cap whatever is at the output from high to low. So it is going the whole cycle of 0 to VDD. And this delay you can work out what is the effective resistance of this MOS, and both of these MOS, what is the delay of charging and discharging. You will size the inverter in such a manner so that the charging and discharging delays are roughly the same. Okay. So now, okay. So now the question, we have a full swing oscillator. How can we tune the frequency of, so the thing which we need to do, tuning frequency of full swing oscillator. Full swing oscillator. So what are the ways to do it? Pardon? So okay, so one way is I can change, so let's say vary VDD. So what am I trying to do here? So let's say I have this inverter. Okay, and this is closed. Sorry, and this is both VDD and grounds are here. Okay, so this is VDD. So if I vary VDD, I am changing the charging and the discharging. I am changing the charging and discharging voltage, and thereby I am varying the time period, T delay of the inverter. So I can do this part, means I can vary the frequency in this manner. What is another way to do it? Let's look at all the possible things. So if you vary VDD, you can always say you can vary ground also. And there is nothing which is stopping me to do that. So in place of using a single inverter, I vary both VDD and ground. So this is ground, but let me just say I vary this and this both from in to out. And this is nothing but also called as a current starved inverter. So I can get some VVP here and VBN here, which I can control. Okay. So using current starved inverter in the ring oscillator is another way to vary frequency. And how can you do this thing? So let me just show you with one single control. Okay. So let's say you have all the chain roughly. Right. So varying the current, I can change the current in both the control the current of the from top and bottom both, and this will control the frequency of the oscillator. Okay. So what is another way of? So let me ask you, because these two things, right? Uh, so if I vary the VDD of the inverter and I do not vary the ground of the inverter, what do you think will happen to the duty cycle of the inverter? Or what do you? So let's put it this way. So in one case, let's say VDD is full, which I am plotting. Okay, and you designed your. Okay, so let's start with the sine wave. So okay, this is the output when VDD was 1. Okay, now I want to change the frequency, and the PMOS and NMOS are sized as per that, such that you have an equal rise and fall time. So if I have equal rise and fall time, means effectively I plotted here sine wave, but what you might be having is something kind of this. Okay, now if I change the VDD, what did I do to the PMOS? So let me. So I kept the ground same. I changed the VDD of this oscillator, and so the drive strength for both PMOS and NMOS have actually changed, right? Means VGS of NMOS and VGS of NMOS and VGS of VSG or PMOS both have changed, in case they do not change in the same manner. So let's look at this one, right? So let me show you here. So when I give a high here, right, the output A discharges ideally like this, right? And this depends on the PMOS strength. And sorry, discharging is through NMOS. Made it wrong here. So it discharges like this, whereas the PMOS charges here. So when you design an inverter at a one particular given frequency, okay, at that time your you try to have an equal charge and discharge time. But in case your PMOS and NMOS strength are not the same, what will be the case? You will have a different discharge cycle and different charge cycle that can affect your duty cycle with respect to the same common mode. What it means is, so let's say this was sitting at 0.5, right? Now when you change the VDD from 1 volt, this is 0. You change your VDD from 1 volt to 0.8, for example. So I came down to 0.8. So I will be now riding at 0.4. So for 0.4, I will have, means if I change the frequency, let's say the frequency becomes half, I may have some kind of this frequency. So, okay, sorry, this has to go to 0.8. So whatever it is, like this. So with respect to the same common mode which you are looking at earlier, 0.5, your duty cycle is gone. Okay. So if you are feeding this clock to some, you feed this clock to any other block, and let's say what you normally may do, you take this clock and you couple it with a full scale inverter with respect to VDD and ground. This VDD you do not change, which is always 1 volt. Okay, you will see a massive duty cycle distortion at the output. So you never do that. You go and actually put an AC coupling cap. So this is to say that when you are changing the VDD of the ring oscillator to vary the oscillation frequency, you should be cautious of what signal I am coupling to in the further circuit, because otherwise you will see a much more duty cycle distortion. The same will not be the case in here. In this case, you are changing the top and bottom both. So if my, so let's say for if I am having 0.1 and 0 volt, in case of the current stub inverter, I may have a 0.9 and 0.1. I may be still sitting at the same common mode voltage with a reduced swing and a reduced frequency. Yeah. No, you are, so the thing is different driving is, so one thing is if you do not take the bulk into account or the PMOS, so you should tie the PMOS bulk. But you can size them only at one particular voltage and one thing. So the thing is the bulk of the PMOS, you should always, so this is the other thing, bulk of the PMOS for the inverter, you tied it to source. Okay, if you do not tie it to source, then you will see a threshold voltage variation. So even when your VDD for both NMOS and PMOS have changed by the same amount, your R doesn't change because the threshold voltage doesn't change. Sorry, your R changes because the threshold voltage changes. The bulk effect you will see. So the two things which I was discussing here, that in the case of a ring inverter which is connected in this manner, one thing is when you change the supply, your actually common mode of the swing goes down, right, with a lower frequency. So you should not couple that thing with any other following buffer circuit directly. Otherwise, you will see a duty cycle distortion. The other thing is, if your drive strength changes, why does it change? It might be due to the bulk effect or any other effect, because now the VDS of the transistors are also changing, right? So if those things come into account, then you will have the then you will have a skewed clock. So in place of a square wave, you may, it's like is from a square, you will see sinus. So let's say you take up any ring oscillator. You can do this experiment. Take a ring oscillator designed at the highest frequency, right? And then you change the supply to the point where it still triggers, the oscillator frequency works. You will see a complete change in the waveforms. You will see square, sinusoidal, triangular, and all the things. And that does happen because of the changing strength of the and the bandwidth of these devices. So but if you look at the other way, the current star one, I am changing the PMOS. Here also I should control. Here you will have two effects. If you do not tie, so this is good in one sense but bad in the other sense. So if you do not tie the bulk, so these both the bulks are there, and here both the bulks are important. So you should tie both these if you have an access to. Then you will see the common mode of this oscillator will not change, ideally. Okay. So these are the two ways in which you can vary the frequency. What is another way of doing it? Where you do not change supply, you do not change. So voltage dependent cap, that is a more tricky part. So let me just go with the switch and cap right now. So I have a switch and a cap. Means what you are saying is also I can do. I'm just saying by having a capacitive loading. Okay. So in case you want a very wide change in the frequency, okay, where you're changing the supply. So let me just give an example that let's say you are using this ring oscillator spanning from 65 nanometer, maybe from 1 gigahertz to 5 gigahertz. It's not easy to get that change by controlling only the supply from. The thing is, the highest frequency of oscillation will be dictated by your supply. How much high can you go? And the lowest frequency of oscillation will be dictated by where your ring oscillator stops triggering at all. So let's say if I keep on reducing this VDD, so if I go close to VTH of this device, it will not trigger VTH of N or VT of PMOS. So you cannot lower the frequency below that point. Now if I still, so it means I cannot trigger trigger any of these switches below a certain frequency or below a certain VDD, but I still want to have a smaller frequency. What shall I do? You use these capacitors to means you still operate at a higher supply voltage, but have a capacitor loading to change the charge and discharge time to have a lower frequency. So if you want to make a very wide range ring oscillator, you can use this supply variation and the capacitor loading combined to have a very wide range. And you can also say this, I can use the capacitor loading to compensate for the process variation, and for the frequency variation I am still going to use VTD. So one thing is, when you add the capacitor, you actually change the power consumption. Adding more capacitor will always come with a more power consumption. Okay, so adding a capacitor at the higher frequency is not at all desirable, and at a lower frequency is also not desirable, but you have to do it because otherwise the switches will not trigger at all. Okay, so this is the way you can tune the ring oscillator. Since I talked of the buffer, so let me show. So you have a ring oscillator. Now I have to connect a buffer. So now the thing is, the VDD of this oscillator, let me call as VDD VCO, is controlled, and I want to convert this oscillator output to full swing. So I will put a buffer whose VDD is same as 1 volt, for example. Okay, and I told that I need to put a cap in between so that I am not restricted by the common mode change at the oscillator output. Right now, who will give the biasing for this with the AC coupling? So the way to do is I can use either this with a resistor. Okay, so you have a coupling cap with a resistor and followed by this. Now this is CAC coupling, this is CP parasitic. So the capture which you are seeing from an oscillator node, this will be a combination of the impedance which you see here. Okay. So shall you use a minimum in CAC captions? No. You should use, because CP is normally low. It will be in terms of few femtofarads. So you should be, so this is a series, if you forget the resistor right now, this is a series combination of CAC and CP, which means the smaller will dominate. So make the captions high enough such that you do not lose from V out till the time V out dash comes here, filtered. If your amplitude is much smaller, then you have to amplify a lot to get the full swing signal. Okay. Now this particular inverter configuration actually, so let me ask you another interesting question here. Now here V into, if you are, let's say if the resistance is very small, which you need for some coupling, then effectively I am connecting something like this, right? Is equal to having, means not equal, which is actually shorting the gate and the drain, putting the inverter in a saturation region. You will see a lot of power consumption. And if you're operating at a very high frequency, the power consumption will be a large. Okay. So a way to do away with that is, in place of using a single inverter connected gate and drain shorted, is to use a ladder of switches same VDD and ground, and I size this accordingly that it is always biased at its midpoint. Okay, now which will have a lesser power consumption? The second one, because you are having too many resistors between VDD and ground. But what is the drawback? Pardon? Rise fall for? No, so the thing is, if I am using this as a diode connected, the just gain is effectively, yeah, but what is the drawback? Yeah, so this one actually comes with a CP2. This actually comes with a larger input cap. Your CP2 is greater than CP1. So the loading on the oscillator will be more, but the power consumption is lesser. So you need to do the trade-off, which is means to a certain extent you can use this. Do not overdo it. Let's say you want to use a 5-chain, things will not even regard. Okay, means what stops me at 3 or 2 or 10, right? So you need to work, see that what works fine. Pardon? No, so the thing is switching power. So there are two things, right? One is the power consumption in this bias itself in comparison to two, and other is the capture loading on the oscillator. So actually, which total power increases? And this is loading at only one node of the oscillator. If you are loading a one node only of the oscillator, then you are causing a asymmetricity in the phases. All the phases will not be equally apart. So you need to check for that too. Okay. So which one? Yeah. Yeah, means that resistance will come into account there. 1 by GM. Yeah. No, 1 by GM and omega. So CP is like 5 femtofarad, right? So the impedance is 1 by, let's you take up the frequency is omega CP and GM. Now it depends on what GM are we working at. So let's say you assume even a 5 femtofarad, 10 power minus 15 and 2 pi. And now what is the frequency we are working at? These are running in gigahertz. So if I pick up something as let's say 5 gigahertz, 25 into 6, 150 into 10 power minus 6. So this is in the order of gigahertz, right? 25 into 6, 150 roughly 10 power. So 10 power 3 by 150 milli ohm or something, right? And what GMs do you work out roughly? So this is close to 6 milliohms. No, so this is giga, right? So giga is 10 power 9 and that is 10 power minus 6, right? Into 150. This is in ohm, means still I convert into milli. So then I have only 150 into 10 power minus 3. This is milli, right? What kind of GMs do you work out? It's like millisiemens. Millisiemens is you will burn quite a good amount of current. So means you when you are using a resistor or any of this inverter thing, you work out what's the net impedance there. So this should be, so if you burn a more power, then you will have the other part whole like going much away. So you will see a lesser loss. But then the power is the main question here, in which you spend in the buffer. Okay, so let's stop here.